Good evening and welcome to the Research Academy. It is Wednesday, March 27th. Nope, sorry, I lied. It's March 26th, 2025. And we are proud to continue to present a series of lectures to help all of us understand research and all of the details within it. So it is indeed, I'm Carol Scheidel. I'm one of the committee members, and I'm happy to be able to host this evening. Dr. Bruce Boynton is going to present for us on validity and reliability are important, testing a test. So to give us some more depth and some more insight. So if everyone would please be sure that they have muted themselves, and also please make sure that your camera is off, as it makes for a much better recording. Bruce, it's all yours. So if you can give us a little bit of introduction, that would be helpful, and take it away.
Okay, and thanks, Carol. We're going to be talking about tests today. We live in a world of tests. And I'm going to talk a little bit about testing, and then get into something called the confusion matrix. It's not really as confusing as it sounds, and that will lead us into discussion of type 1 and type 2 errors, multiple comparisons problem, prevalence and incidence, and a little bit scattered here and there about psychological tests and how they're validated both by statisticians and by psychologists. Okay, we live in a world, in fact, our world is just filled with tests. There's the IQ test, the test that you take to get into college, SAT or ACT, the GRE, TB skin test, all the tests that they do at the hospital, home COVID tests, the dipsticks, glucose tests if you're diabetic, and all the psychological tests. But what do these tests really mean, and how good are they? For instance, does my IQ score tell how smart I am? No. How accurate is the home COVID test? Well, you remember, maybe they're getting better, but they used to say, if you got a negative, just do it again. Does GRE predict how well I'll do in graduate school? No. Is my serum sodium is high on the lab test? Is it okay? Probably is. The skin tests are positive. Do I have TB? Maybe not. And do these psychological tests really mean anything? So we're going to get into all the different aspects of tests and how to test a test. Now, these are some validated psychological tests that are used in a lot of aromatherapy studies. Anxiety, we have the generalized anxiety disorder test, the GAD-7, the Zoom self-rating anxiety scale, the state trait anxiety inventory. There's different tests for pain. You're probably familiar with the visual analog scale with the little faces. And there's another, a brief pain inventory for depression. Sometimes you might ask, do we really know what depression is? Do we really know what anxiety is? How do we formulate a test that really measures that? And sometimes what the experimenter wants to determine, there's no test for. As an example, Dr. Marnie Raven, she wanted a measure of ease. Well, there was no measure of ease. And so what she had to do was to go to a subscale of the comfort test, which measured ease. Now, how do psychologists go about validating psychological measurements? One is called validity. And what validity measures is, does the test measure what it's intended to measure? For instance, does it ask does ask questions about depression or anxiety or whatever you're trying to measure. Is the test reliable? That has to do with if you take the test one day and then you take the test the next week, the test scores should be somehow related. If they're wildly different, then that test may not be reliable. Measurement and variance. Do the test questions measure the same thing across different groups? I'll give you a sort of a funny example of that. They are using some of the IQ tests on these gorillas or different kinds of simian species, and they perform them exactly the same as they would in a human. And do they get the same thing? An interesting example of this is they had several pictures of, and the question was, where would you go if you're afraid? And they had a house and a schoolyard and a tree. Well, the gorilla put tree, which is perfectly reasonable, but it was wrong for humans to put tree. Standardization. The test administration and scoring must be consistent. For instance, if everyone gives the test differently and they score it differently, well, you have no reliability or confidence in that test. And finally, the theoretical framework. Does the test comport with what we know about depression or what we know about anxiety or what we know about pain? Okay, this is the confusion matrix. It's 2 by 2, so there's 2 rows and 2 columns. And at the top, it's labeled true class. Well, what's true class? That means it could mean whether you do or do not have a disease, or whether you can or cannot identify a particular fruit, or whether you can or cannot smell a certain aroma. And in the true class, all this column, under positive, all this column is really true. It really is true. And all this column, under negative, really is false. Now, on the left is what your test predicted. So under positive, the test predicted positive for all these observations. Some of them it got right, and some of them it did not get right. Likewise, the test predicted all these observations are negative. Some were truly negative, and some were mistakes, false negatives. So in the dark blue squares are the observations that really were positive and the tests predicted were positive. And here we really were negative and the test predicted that they were negative. So these lighter blue squares are mistakes, false positives. So it really was negative, but the test said it was positive. Down here, false negatives, it really was positive, but the test said it was negative. Okay, and we're going to, for simplicity, just use these abbreviations: TP for true positive, pretty obvious, FP for false positive, and so forth and so on. Okay, why is it called a confusion matrix? It seems pretty simple. Well, think about a larger set. Now, this is a 3 by 3 matrix. It has 3 rows and 3 columns. And this, I just labeled this arbitrarily: lemon, orange, and tangerine. You might think it's maybe the predicted class is what a child says, a young child who you're trying to teach. And this is what it really is. So Now you notice that this diagonal, the one in green here, is it really was a lemon, and the child predicted it was a lemon. Here, it really was an orange, and the child said it's an orange. And here, it really was a tangerine, and the child said it was a tangerine. So all this diagonal are correct answers. So all of these are either false positives or false negatives. Okay, imagine now a matrix with 20 rows and 20 columns. So that's going to be 20 times 20, 400 boxes. And all but 20 of those boxes are going to be false positives and false negatives. So you see how you can get confused. The other way that you can get confused is have these labels in the wrong place. So I always put true class, what it really is, at the top, and predicted class on the left-hand side, although you will see it other ways. Either way is right, but if you get confused and put it wrong, everything will be screwed up. So that's why I always put true class at the top. Okay, at this point, you may think that all the confusion of the confusion matrix is in your head, and what does this have to do with aromatherapy anyhow? And I'm going to show you a couple of articles in which they use the confusion matrix. These folks made a device, complicated looking device, to detect adulteration in Cistus ladanifer essential oil. And Cistus ladanifer is a form of rock rose. And so what these authors did was they took some essential oil and they put extra jojoba, or they took essential oils and put synthetic ingredients and so forth and so on. And then they used the confusion matrix to determine how good their device was at detecting adulteration. Here's another example. This is a classification of bitter orange essential oils according to the stage of fruit ripening. So these investigators noticed that the GCMS of the essential oil would change over the period in the fall. And so they made a test to predict what that essential oil was going to look like, and then used a confusion matrix to determine how good their test was. So this has 4 by 4, so that's 16 squares. And again, this diagonal is all the correct answers. Now, they don't have the observations in counting form, like simple numbers. They put it in percent. But if you look at this, 80%, 86%, 84%, 76%, and you look at these, nothing was wrong here, and very small amounts in most of the other boxes. So this is a pretty good test. Okay, now we're going to examine a test, and we want to determine the accuracy, the sensitivity, the specificity, and positive and negative predictive value of this test. Now, what are they anyhow? Well, it's just the usual thought about accuracy. Out of the total things that you had to predict with your test, how many did the test predict correctly? That's our usual idea of accuracy. And we'll use this with the confusion matrix right here. So you remember the dark blue squares are the correct predictions. The light blue squares are errors. So if you think about what the test got right, it's this true positives plus the true negatives over everything. This is everything. So it'll be TP right here plus TN over everything. So let's try that out. Okay. Now I just arbitrarily put 5s in all these boxes to do a little fake calculation. So let's figure the accuracy. It's the true positives and the true negatives. So that's 5 plus 5 is 10 over everything. 5, 10, 15, 20. So 10 over 20, that's 50%. So that's not a very accurate test. What does sensitivity mean? Well, sensitivity is the proportion of the actual positives, what were really positive. What proportion of those actual positives did the test correctly identify? Okay, so we said that the true class is what is really going on. So all the positives are right here. So everything in this column is positive. Our test got some of them right and some of them wrong. Let's calculate the proportion of true positives that the test got right. Well, that's true positives over everything in this column, which is true positives plus false negatives. So 5 over 5 plus 5 is 5 over 10, which again is 50%. So it's not very accurate at predicting true positives. What about specificity? What proportion of the actual negatives did the test identify? Okay, now you remember when we calculated sensitivity, we worked in this column on all the really positives. And for specificity, we're going to work in this column, all the truly negatives. Well, if we want an accurate test, it's going to be, not accurate, a specific test, it's going to correctly identify the true negatives. So let's put the true negatives, here we have 8 over everything in this column. 8 plus 2 is 10. So 8 over 10 is 80%. That's pretty specific. It's accurate. 4 times out of 5, it will correctly identify if you do not have the condition. Well, what the heck are positive predictive values? Well, that positive predictive value is what proportion of the predicted positives are true positives. Well, what does that mean? What's the value of a positive test? Or you might say it, if I get a positive test, how confident am I that the test is truly positive? So if you get let's say you get you're given a battery of tests at the lab, and one of them turns out outside the normal limits. Is that really positive? Should I be worried about that? Or can that just happen by chance? Well, that's where the positive predictive value comes in. Okay, now remember when we calculated sensitivity, the ability to pick up true positives, we worked in this column. And when we investigated specificity, the ability of the test to pick up true negatives, we worked in this column. So to figure out positive predictive value, we work in this row. So everything in this row, our test said was positive. Some of them were really positive, were true positives, and some of them we made a mistake. So just working in this row for positive predictive value, we'll have 7 over 7 plus 4, everything in this row, is 7 over 11, which is 63.6%. So if you get a positive from this particular test, about 2/3 of the time, it will be a true positive. But then 1/3 of the time, it was really negative, and your test called it was positive. Okay, what about negative predictive value? Well, that's what proportion of predicted negatives are true negatives. Or in other words, what's the value of a negative test? Or if my test is negative, am I confident that it's truly negative? Let's go back to the home COVID test. If you had a fever and cough and body aches, if you got a negative test, the authorities would tell you to take a test again the next day or in 2 days. So that test must have not had a good negative predictive value because we weren't confident that it was truly negative. And again, we worked in this row to figure positive predictive value, the ability of the test to determine true positives, and we'll work in this row here. Everything in this row was predicted to be negative by the test. Some of them it got right, were truly negative, and some of them were false negatives. So it's TN, true negatives, over everything in this row, true negatives plus false negatives. Okay, now can you use this to calculate things about a psychological test? Well, how do you know if someone is truly depressed? Or how do you know if they're truly anxious, or they're truly stressed, or they're truly at comfort? Well, one of the things you can do is to test let's say you are not happy with the existing test and think that you can design a better test. Then you can test that test against that gold standard measurement and see where they differ. And here I've just filled in some arbitrary numbers. Let's figure out the accuracy. So remember, that's everything that's true positives and true negatives. So that's 7 and plus 8 is 15 over everything in this, all these 4 boxes. So 8 and 2 is 10, 7 and 3 is 10, 10 and 10 is 20. So it got 15 out of 20 correctly. That was its accuracy, 75%. Let's look at sensitivity. All right, sensitivity, remember we work in this column right here, and we're going to put true positives over everything in this column, which is true positives plus false negatives. So it's 8 over 8 plus 3, it's 8 over 11, 89%. So pretty sensitive. This is a pretty sensitive test. Okay, and we can do the same thing for specificity. We work in this column for specificity. And remember, it's the true negatives over the true negatives plus the false positives. So 7 over 7 plus 2 is 9. 7 over 9, 77.8%. And you can figure the positive predictive value as we showed before. Okay, and here is a little chart for y'all so that you don't have to recreate from memory all these values. And I have put a PDF that has this chart and some other formulas and things, and that should be available to you just for your reference, so you won't have to remember or take notes or anything. All right, what does all this stuff have to do with type 1 and type 2 error? Well, there are two kinds of errors in conducting a test. Type 1 error is you predict something, but it does not occur. An example would be you look at a GCMS and you predict that it's lavender, but it's really spike lavender. This is a false positive result, and it's represented by the Greek letter alpha. And you'll see alpha in almost every academic paper on aromatherapy, and we'll tell you how. Type 2 error is less talked about, but it should be more. Type 2 error is you fail to predict something that does occur. That's a false negative result, and it's represented by the Greek letter beta. I'm going to give you some examples here. Going back to our confusion matrix, we said type 1 errors are false positives. Well, it fits right in here. And type 2 errors are false negatives. So you understand how it relates to this matrix. Type 1 error is you call something positive when it's really negative. Type 2 error is you call something negative when it's really positive. And we'll have some dramatic examples of that in just a second. Here we go. Examines the man's abdomen and says, "You're pregnant." Here, the woman is examining a woman who's obviously pregnant, and she concludes you're not pregnant. So the first is a type 1 error, the second a type 2 error. Okay, the probability of making, I said it was a type 1 error, but it's really the probability of making a type 1 error is alpha. So when you see in a manuscript, we tested this and it was significant at the p is less than 0.05. What does that mean? It means there was less than 5 chances in 100 of making a type 1 error. Now, what's in less articles is the probability of making a type 2 error, which is beta. So alpha is usually set at about 0.05. Beta is usually set at about 0.2. So, oh, I made a mistake here. Well, it's this. What this actually says is there's less than 20 chances in 100 of a type 2 error. Now, if you subtract beta from 1, this is called the power of the test, the power to determine differences. And this beta is usually set at 0.2, so that means 1 minus beta is is 0.8, which means there's an 80% chance of detecting a difference if that difference exists. Okay, let's show some examples of aromatherapy papers where they have discussed type 1 and type 2 eras. This is an interesting paper from back in 2014. Consumers' acceptability of beef from animals supplemented with essential oils. I guess they fed these cattle essential oils and see how good the beef is. But they said diet effect, inclusion of essential oils, was a significant factor for tenderness and flavor acceptability. P is less than or equal to 0.01. So this means that there was less or equal to 1 in 100 chances of making a type 1 error. That is saying that there was a significant factor. So a type 1 error would be there is a significant factor when in fact there's not. So they concluded that feeding essential oils to cattle or dumping them on the beef or whatever they did was a significant factor for tenderness and flavor acceptability. Okay, type 2 error. This is from a paper by Jesse Hawkins. And type 2 error has to do with sample size. Sample size was determined by conducting a power analysis. Remember, 1 minus beta is called power. A power analysis using, now this is just some app or some little program that figures out power for you. To achieve a 80% power, so that means 1 minus beta is 80%. That means the chance of making a type 2 error is 20%. Okay, so she also brings in alpha, which is the risk of making a type 1 error of 0.05. So to get an 80% power to detect the difference that she's interested in with an alpha of 0.05, she's going to need 36 participants required to detect a large effect on total fatigue. So these kinds of analyses are definitely out there in aromatherapy articles. Okay, there's some other factors that can affect your test results, but we don't think about them as much. And they're the multiple comparisons problem and the prevalence of the condition. All right, the multiple comparisons problem. No matter how accurate your test, if you do enough of them, you're going to get false positives. And here's a little question. If we do 100 tests at the alpha equals 0.05 level, so the risk of calling something positive when it's really negative is only 5%, 1 out of 20, 5 out of 100. How many of these 100 tests will be positive, not because there was a real difference, but just due to random variation? Anyone have any idea? Any thoughts? It's 5. All you got to do is multiply 100 times alpha. So 100, you will move the decimal point 2 places to the right. So that's 5. Now, here's another question. If we expect 5 positive results in 100 tests and we get 5 positive results, how much confidence do we have in each test result? Well, you don't have any confidence. That's what you would expect from just random variation. And to determine if anything is really truly positive, you have to do further tests, which I won't go into here, like analysis variance, Tukey's test, Bonferroni's, and so forth and so on. Okay, so here's an example. A lot of people come to me and they've had a whole battery of tests from the lab, and something is out of whack. That's what you expect. That's just what you expect from random variation. You don't have much confidence in the individual positive. Here's another example. Suppose, I'll do that one later. Prevalence and incidence. Prevalence is the proportion of the population that has a condition. Here's an example. 19.1% of US adults have anxiety. So if we were going to cure anxiety in everyone in the United States, we'd have more than 40 million clients. So it's a very common disorder. Incidence is a measure of risk, the risk of getting the condition. For example, the risk of US inhabitants becoming COVID positive was 4.3% in the week that ended on 22 February 25. So that was their risk, 4.3%. So the terms incidence and prevalence are often confused. If you're talking about the proportion of the population that has something right now, that's prevalence. If you talk about the risk of getting it in the future, that's incidence. Okay. Now, can the prevalence of a condition change our analysis of the test? I got two answers possible. No, this is a mathematical formula. Nothing outside the matrix makes any difference. You just do the calculation. Or, yes, increasing prevalence makes false positives less common, and decreasing prevalence makes false positives more common. Anyone have any ideas? Well,
Melanie
yes.
Schiffman says yes.
Okay. Well, she's right. She's right. Here, think about it like this. Suppose you develop the best test in the world for smallpox. It's just so accurate. And you do a bunch of smallpox tests, and all you get is false positives. Why is that? How can that be? This is the best test. The answer is there ain't no smallpox. It's an extinct disease. Nobody has smallpox. So no one can go in the true positive box because there's no smallpox. So all positives will be false positives. So increasing prevalence, let's think of increasing prevalence. What's an example? When you have a pandemic like we had with COVID. So no matter what your test said, the clinicians wanted to see you or wanted you to do something or stay home or put on a mask or something during that COVID pandemic, no matter what your test said. Decreasing prevalence, so if the condition is decreasing in prevalence, there's fewer and fewer people that have it. So it makes your false positives more common. Okay, what we've covered. We talked about how to calculate accuracy, sensitivity, specificity, and positive and negative predictive value. We talked about type 1 and type 2 errors. Type 1 errors are false positives. Type 2 errors are false negatives. The multiple comparisons problem. False positives will occur with any test. The more tests you do, the more false positives you're going to get with any test. We talked about prevalence, which is the percent of the population with the condition, and incidence, the risk of acquiring the condition, and the validation of psychological tests. Here's a couple of articles that you might want to check out on the multiple comparisons problem and to get really clear on type 1 and type 2 errors. And any questions?
You're certainly welcome to unmute yourself and share any questions or comments. Got a comment in our chat, which is super presentation. Thank you so much, Bruce. That's from Melanie Schiffman.
Thank you.
Denise has added a heart to that one. And back when you asked the question about the number, both Marnie and Melanie Schiffman had posted in the chat of 5. So they were correct right along with you.
Good for you. That's excellent, because it confuses even public health officials. I know this from experience. Okay. Well, if there are no questions,
wait, I got a couple. Let me see. We got 3 new comments. Let's see. Another. This was super helpful and interesting. Thank you so much. From Mimi Russell, DeMartine, Catherine Gentile. I got a where I just crowd. Thank you, Cheryl Beryl. Beller Kenner says, great clarity, thank you. Susui Chang says, thank you so much. Colleen says, thank you. Denise, excellent presentation. Aaron Stewart is also thanking you for the presentation. Serene is truly a revelation. And Martha, Mimi asks again, when will the recording be available? And yes, the recording will be available. It'll take us, it should be up on the Research Academy website probably within a week, maybe even less, which would be great. But we just have to clean up the recording and get it posted. And I'm going to stop the recording since.
And
That wraps up today's session. Thanks for tuning into the AIA Research Academy. This academy exists thanks to the generous support of the Gaffasi Foundation and is here to make aromatherapy research fun, accessible, and relevant. Our mission is simple yet powerful: to educate, inspire, and connect a global community committed to advancing the science of aromatherapy. We envision a future where research is not just part of the conversation, but the culture. The best part, access is completely free. Simply sign up through the link in the description box below. And if you're an AIA member, the Academy is already part of your member benefits, putting powerful resources right at your fingertips. If you're passionate about deepening your understanding of aromatherapy through research, you're in the right place. Be sure to subscribe and hit the notification bell to stay connected with our latest sessions. We appreciate your curiosity, your time, and your commitment to learning.